All right, my name is Stefan Thomas. I'm CTO at Ripple Incorporated, and I want to talk to you today a little bit about consensus. And it seems very poignant to be giving this talk at Consensus, and so I'm very excited to give this presentation, as well as it has a bunch of content in it that has been sort of burning under my nails for quite a few years, but we've never really been able to talk about it. It's never really the right time, or we've never had the right presentation to fit this content, so I'm quite excited to share it with you guys today. And also, I really like this setup. It's almost like having a couch. So welcome to my living room. Let's chat about consensus. Here's some of the topics I'm going to cover. So first, I want to explain what is consensus, and then talk about some approaches. And then finally, we want to know which one's the best one. How do we evaluate different approaches for different use cases? And then towards the end, I want to also tease what happens beyond consensus. And I don't know if we all have time for questions, but I put it in there anyway. So what is consensus? If you look it up in the dictionary, obligatory dictionary slide, it just says that it's some sort of general agreement. So you can kind of think of it as, let's say you have an orchestra. The fact that they're all playing the same piece of music is kind of important for the music to sound good. And so consensus is that principle. It's this sort of, we all know what we're doing, we all agree what we're doing, and as a result, there's no friction with what we're doing. So what do you need this for? What do you use consensus for? It's actually much broader than just technology. So think of something very practical, like you're going to the supermarket, you're shopping. There's a couple of things that you need for that experience to happen, for that to be practical in society. First thing is you need some sort of rules of trading, right? Like, well, I get to go in and I get to take things off the shelf and I get to put them in my cart, and then at the end I pay when I leave. These are all sort of unwritten rules, but there's also a bunch of more formal things, like you need a currency that store actually accepts, and we need to come to consensus of what currency we're going to use. Which currency am I going to expect that a store actually accepts, so that's the one I'm going to carry in my pocket. We have to agree on something like property rights. Like once I buy this lettuce, it's my lettuce. You can't just come and take it. And if you do, we have to have some sort of dispute resolution, some way for me to get it back, or for me to come after you for taking my lettuce. And so consensus is really what gives all these kinds of rules and laws their power. It's the thing that takes something from being just a sentence that somebody decided to write down to something that's legal, that's really enforced. And so the methods that we use to come to consensus are quite important. They're at the root of everything from politics to blockchain. So let's look at some examples of how people have come to consensus historically, right? So let's take the simplest example. You have some little island, you have some islanders on it. And in order to set some rules, one of them declares themselves king. And now they set all the rules. Well, what happens? Well, of course, everyone else is going to be jealous. And pretty soon there's going to be some conflict, and then you might have a new king. And so it's not a very stable system. We can do better. So the way that most of us come to consensus, at least the ones that are lucky enough to live in a democracy, is that we get to vote, and then sometimes our candidate wins and sometimes our candidate loses. And depending on that, we'll have a result. And whether we like it or not, we'll have to accept what that result was. And so we agree to that, sometimes grudgingly, but we agree to that for the sake of not being at each other's throat all the time. And that's a quite scalable process. There are some fairly large democracies, and it's being used for some fairly large sort of non-governmental organizations and so on. So it's a very powerful little concept. There's a couple nuances I want to highlight. So first of all, there's this concept of suffrage, which means not everyone gets to vote all the time. So we haven't had universal suffrage for all of history, as I'm sure you know. So you have to, with any democracy, you have to define like who actually gets to vote. And once we start talking about some of the more advanced systems like blockchains, you also have to decide the weighting. I think with democracy, very often we talk about one person, one vote. But I think with blockchains, it's more often that it's weighted in some way based on, not to go too far ahead, but mining power, et cetera. The next thing that we have to keep in mind is that there's a difference between the theory of any kind of system of governments or any kind of system of consensus and the actual practice of it. So very often you'll have these great proclamations of like, well, everyone should get to vote and everyone should vote. But then in practice, there's voter registration laws, and there's like all kinds of difficulties with voting machines, and how do you trust them, and so on. So it's actually quite difficult to put some of these processes into practice, and it's no different with blockchains, where like you have some idea of who you want to have the control and the governance in your blockchain, but actually putting that into practice is quite another matter. So finally, let's talk about some blockchains. This is probably what you're here for. So first of all, I want to cover classical consensus. So this is kind of what's been around the longest. Paxos was published in 1989. This is a paper by Leslie Lamport that describes a form of agreement that is very reliable to certain guarantees. And there have been many, many other papers of sort of building on top of that. And the basic idea is that every participant gets to vote. There are obviously weighted schemes, but the basic idea is that every participant gets to vote. But the problem that you run into with a lot of these systems is that, well, who's a participant? Let's say you have 4 participants and they're each voting, but somebody gets outvoted, and so they decide to spin up a bunch more nodes so that they get a majority, and now suddenly they're in the majority and everyone else is kind of like, wait, what? And so you have to kind of close the system off. You can't have classical consensus where just anybody can join and start participating, because anyone could just do what's called a Sybil attack, which is spinning up lots of fake nodes to try to outvote everyone else. But once you close it off, it's kind of difficult for other people to join. It's not really the kind of open blockchain that we would like. And so there have been a number of new approaches that have come up following Bitcoin. So let's start with Bitcoin itself. So the idea there is that you get to vote proportional to your effort at a mathematical puzzle. That's essentially what it boils down to. And again, this is the theory of it. In practice, it's a lot more complicated, but I only have 13 minutes remaining, so can't really get into too much detail. But essentially, you get to vote based on the power of how much power you can put into this mathematical puzzle. And so one of the issues that we're seeing play out right now is that it wasn't really intended that way, at least I don't think so, but the majority of mining power is actually with professional miners. So like it was originally intended that everyone would run the software and everyone would mine a little bit, but it has completely professionalized, right? Like today, if you try to mine, you're not going to have a good time. You're not going to make a profit. And so the vast majority of people has actually very little mining power. It's professional miners that control the majority of that mining power. And so that makes it very difficult to do things like rule changes, because they can only get passed if the miners are in favor of them. So if you want to do anything that lowers transaction fees, for example, good luck. So the second problem that a lot of people have highlighted is the energy consumption of that approach. So Bitcoin consumes something around like 300 megawatts is actually the most conservative estimate that I found. There are a lot of bigger numbers. And if you look at the CO2 output of that corresponds to around 2 million metric tons of CO2. And it's kind of hard to get your head around that kind of number, but it's a lot. And it's probably more than we'd want for something of the complexity of a ledger that's used by the number of people that Bitcoin is used by. So it doesn't seem like maybe the most efficient way of doing it, but it's certainly a way it works. The next model that's been proposed is proof of stake, and this was proposed in part to address some of the previous concerns, namely we want to be able to have the people that are actually participating in the network vote, and then also we want to have them vote without having to do all this energy wasting work first. And so the main criticism that people have raised for proof of stake is the fact that it has sort of a circular definition. If I want to know the state of the network, I basically have to trace that arrow back and have to look at who has the vote, like who gets to vote how much. In order to know that, we need to know how the currency is distributed currently, and so we trace it back, and well, that depends on the state of the network. And so you can do it if you bootstrap it somehow, but you can't just start with a proof of stake system right away, right? So you have to bootstrap it with either some initial distribution that's sort of hard-coded or something like that. And as a result, a lot of people have proposed sort of mixed schemes where they combine proof of stake with other systems, or they add things on top of proof of stake. But I think some of the approaches are more obscuring the problem than actually solving it. I think there are some credible approaches, but it's definitely a very complex way of doing it. And just to complete our survey, you see probably the little Ripple pin. So one other method is the Ripple consensus algorithm. And so the way that works is that everyone gets a vote in a user-defined topology. And I want to spend a few slides just explaining how Ripple consensus actually works, because I think there's compared to proof of stake and proof of work, very little awareness of how it actually works out there. So the basic idea is to go back to the fundamentals of consensus. Like who do I actually want to be in consensus with? And the answer is quite interesting. It's the people that I transact with. Because if you remember that supermarket example, consensus is ultimately so that we can transact with each other, so we can interact with each other. And so the people that I need to be in consensus with are the people that I end up interacting with. And so that's where we start. We say, let's everybody just write down who you're interacting with and who you want to be in consensus with so that you can interact. Okay, so that gives us some sort of graph, some sort of structure. And now that structure is probably too loosely connected to run a proper consensus algorithm like classical consensus. And so what we need to do is we need to ask people to add more connections in there. So like if you look at this topology, and this would be a public topology that anyone can look at it, you would want to add more connections to it. So people go and they add connections one at a time. And so that strengthens the topology until eventually you can come to consensus. Now, one really important thing about consensus is that it's always voluntary. Like if I want to not believe in the American legal system and completely be outside of it, and I declare myself my own sovereign nation, I can do that. There will probably be repercussions in this case because of, these are laws that are actually being enforced, violently enforced. But ultimately, you can still not force me to agree to it, right? Like I'm the king of my own head, so to speak. And if there's no enforcement, which is the case with blockchains, it's even stronger in that like we can't force anyone to join the Ripple network. We can't force anyone to join our version of the Ripple network. And so consensus is always voluntary. So if you have these people that are expressing who they want to transact with, and that topology can't be strengthened to a point where it comes to one singular consensus, that just means that there are multiple fragments of that out there. However, anyone who does want that singular consensus can achieve it just by creating more connections, or can help achieve it just by creating more connections. So the people that are in that sort of branch or in that sort of fork are only the people that are intentionally not participating, if that makes sense. And so it's kind of an evolutionary system where like you have people interacting, and so they build more connections, and that's how you create a system that's connected enough. Once you have that topology that's well enough connected, the actual consensus algorithm itself is fairly simple. So it's just a sort of avalanche opinion algorithm. So you basically have everybody state their initial opinion about a transaction, and then you default to no, we're not going to do that transaction, and if there are enough people in favor of the transaction, you do it. And if you end up voting no, but the transaction is still considered valid, you do it again next round with a better chance of success. It could have just been the transaction got submitted too late. That part is not as interesting to talk about. It's pretty straightforward. So let's compare some of these approaches and talk about some of the pros and cons. So first of all, let's use real metrics from real networks. So I picked a couple of networks to compare. There's Bitcoin, there's Ripple, Ethereum, and NEM. These are some of the largest digital assets. NEM, if you're not familiar with it, is a proof of stake system. So this is one, well, they actually call it proof of interest, but it is fundamentally a proof of stake system. And so here I've looked at the average delay between ledgers or blocks as of Friday. So basically I sampled one day and I looked at the average delay. So you can see because we know the topology in Ripple, we can actually come to consensus very quickly. We don't have to have very wide delay between blocks. And the way that looks, if you actually plot it, is so you can see Ripple, every line represents one new ledger. This is a 1 hour period that I've drawn here. Then you see Ethereum every block, you see NEM every block, and you see Bitcoin every block. So Bitcoin during that 1 hour sample period created 4 blocks, and you can see them sort of as little lines there. And in order to actually compare the proof of work to the Ripple consensus, I'm going to zoom in on a portion of that graph, which is the first 15 minutes. And we're going to kind of pull that out a little bit. So as you can see, Ripple has sort of this very, almost like a rhythm. It's like very evenly spaced. And then Ethereum is kind of random. And that's no coincidence. That's because the way that proof of work works is that people find blocks at random times. So there's sort of a probability to find a block, but it's not guaranteed to happen at a specific moment. And so you get this jitter, you get this randomness. Sometimes there are 2 blocks that are just seconds apart, and sometimes you don't find a block for minutes. And so with Ripple, because we know who the validators are, they can actually, they know when they have to vote on a new ledger and when they have to close a new ledger, so you get that nicer cadence, which is good property for something like a payment system, because then you can have a guarantee as to how fast your payments are going to be processed. So this is, to express that mathematically, I've taken a standard deviation. So you can see that for a lot of proof-of-work blockchains, the standard deviation is actually bigger than the delay. So there's a huge variance. It's completely random. And then for something like Ripple, you have that cadence where the difference between block intervals is actually very small. And that's a good property to have. Another point I wanted to make is that proof of work actually requires multiple confirmations. And the reason for that is that there is sort of an open space where like new people could have blocks you haven't heard of. And so even something that got confirmed could still be reversed. And what that means for you as someone who's transaction processing is like that's obviously pretty bad if that happens. So let's say someone deposits money with your exchange, you process that payment, they withdraw it, then suddenly it gets reversed, you're in big trouble, you've lost that money. And so that's something that you want to avoid if possible. But you can't really ultimately eliminate it. So what happens in cryptocurrencies is that or in proof of work systems is that you just wait enough blocks that you feel pretty confident it's not going to get reversed. And there is a exponential relationship between how many blocks you wait and how likely it is to get reversed, or like an inverse exponential relationship. On the other hand, if you know who the validators are up front, based on the topology of the network, you know exactly who's voting. And so even just one ledger gives you finality. So whereas in Bitcoin, if you write a Bitcoin implementation, as I have done, you have to write what's called a chain reorganization code, which is what happens when you get a longer chain than what you thought it was. And so you have to undo some transactions and redo other ones. We don't have that in Ripple, because once a ledger is voted on by a validator, that validator can't change its mind. And the set of validators that you're particularly listened to is hard-coded. It's hard configured when you set up your node. And so, yeah, we don't have any ambiguity. Once a transaction is validated, it's fully validated, we know it's fully validated based on the people that we want to transact with, our environment. What that does to the kind of delay is, that means with Ripple you have to wait for exactly one delay. Ethereum, sort of the number that's being thrown around by some of the Ethereum advocates is 12 confirmations. So you have to wait for 12 blocks if you want to be absolutely sure. And so that adds to the differential in how long you have to actually wait to process a transaction. So that's kind of the final assessment on the speed. One other point I wanted to make is the actual choice of validators. So this is a picture of a validator in China, a Bitcoin miner in China. And so the main incentive for Bitcoin miners is just to be as cheap as they could possibly be at mining Bitcoins. Okay, so they don't care about much else. They care about how cheaply can we mine these Bitcoins. And what that does is it leaves out a lot of other metrics that you might care about for a validator of your blockchain, like how good is their uptime? Because if a lot of miners get taken down all at once, then suddenly it's very difficult to confirm a Bitcoin transaction, because there's no new blocks being generated, and it takes a long time for the difficulty to come down to adjust. And so you get these operations that are just set up as like bare bones affairs with like just mining equipment and then like bare bones power. Again, this is the same mining operation. These are pictures from the New York Times. And so with Ripple Consensus, since the validators are actually chosen by the users, it gives a slightly different incentive. So users, they want all kinds of properties out of a validator. They might want security. They might want that validator to be fast enough to process a lot of transactions. They might want a lot of uptime, and so on. And so I've taken some pictures from one of our actual validators on the Ripple network at Tokyo. And I was just in Japan actually to visit their data center. And it's like it is the state-of-the-art data center. It's like the best one I've ever seen. They have the little vein scanners where it like checks your vein pattern when you go in, and all the kind of redundancy that you would expect. And so it's a very different kind of platform to run your blockchain on. These are some of the racks. The actual server room that the Ripple validator is in has not been down ever since it was built in 2001. Zero downtime. So beyond blockchain, there is actually a couple of things that you can do. So if you don't want the whole world to always be on consensus all the time, you can do a couple of other approaches. You don't always want consensus. Diversity is a good thing too. And so people have started to suggest some different approaches. So with consensus, you have everyone in agreement. Alternatives are you can have just agreeing on particular transactions. And then there's another approach which we call interledger, where you have different people that are part of different groups and so on. Don't have time to get into any of that. So with that, I'm going to wrap it up and hand it over to Mark, who's going to talk about smart contracts. Thank you, guys.
Thanks. All right, thanks, Stefan. So thanks very much for coming. And if you're interested in the problem I'm going to talk about, my name's Mark Staples. I'm from Data61. I'm going to talk about formal specification verification of smart contracts. So first, briefly, what is Data61? It's a national research institution. It's part of CSIRO, which does all sorts of research in mining and agriculture. Data61 is the digital innovation research piece of that. We're about 1,100 people, including about 400 PhD students. So we do a lot of sort of academic style research, but we have deep partnerships with a lot of universities in Australia and government and industry in Australia. And because we're so big, we really have quite a broad scope. So the whole data pipeline from sensing through to communications and AI and ML and so on. But today I'm going to talk about blockchain research. So we're doing a few different pieces of blockchain research at Data61. We're not looking at research so much at the platform level, but more at the sort of the middleware level, how you build systems on top of different blockchain systems. So we're looking at issues about how you design blockchain-based system, design trade-offs. We're looking at how you can use smart contracts, both to support legal contracts, but also to support other kinds of things like inter-organizational process coordination. And we're looking at issues, which I'll talk about mostly today, around how you can get evidence that a blockchain-based system is going to do what you think it should do. So we're using empirical techniques, so testing and monitoring of live systems, but also formal mathematical techniques for reasoning about the behavior of blockchain-based systems, and that's the focus for today. So why is this important? Why do we care about trustworthy blockchain-based systems? We care about it because we're relying on these systems, or increasingly going to do that more and more. So, you know, we've already seen with the DAO failure, when that failed, that hurt, and the direct cost is sort of debatable, but there was a sort of a large cost, and it also led to the fork, which was a bad thing. Most of us are here because there's huge potential economic value in having these blockchain-based systems. If there's no value, then why are we here for many of us? So, and that can be in supply chain, asset registries, there's a whole range of different use cases. But because there's so much economic value, if the blockchain-based systems fail, that's going to cause a whole lot of pain for people relying on those systems. But it's not just economic value. Increasingly, there's a lot of security-critical and safety-critical use cases being put on blockchain. And so there, if the blockchain-based systems fail, then people can get hurt or die. So we want to have systems that work. So it brings me to talk about trust. There's a lot of talk about trust in and around blockchain-based systems, blockchains. So Dependable Software Systems has a view on what trust is. So a trusted system is one that you've placed your trust in. You've chosen to rely on it to achieve some goal. And when it fails, you suffer some kind of harm or loss. On the other hand, a trustworthy system is one where you have evidence that it's not going to fail. So here, trust means accepting exposure to risk. And so I always think it's amusing when law firms or professional services firms go out and say, we want to be your trusted advisor, because what they're saying is, we want to be in a position to hurt you should we fail. So what you really want is a trustworthy advisor. So formal specification verification. There's been a dream since the 60s to try and do formal specification verification of real-world systems. It's about using mathematics and logical techniques to reason about all the possible behaviors of software. So you're not just testing a few individual use cases, a few test cases. This can provide the kind of strongest form of evidence that the logic of the software is correct, that it's going to do exactly what it should do in the specification. And this is the schema about how it works. You have some real code, and you have a specification. The real code is going to run on a physical system, real-world hardware, and the specification that you've written down is meant to capture the needs in the usage environment for the system. I just lost my screen. So there's mathematical counterparts for that. So we have the mathematical counterpart for the formal specification, which is meant to be capture what the needs are in a mathematical form. And there's also the code, the semantics of the code, which we've also captured in logic. And then you have a verification proof that those two are consistent, that every possible behavior allowed by the code, allowed by the formal specification, that every possible behavior possible in the code is allowed by the formal specification. So it's been a dream since the 60s. There was a milestone formal verification done by Data61, which was at the time called NICTA, for the SEL4 embedded systems microkernel. It was a high-performance embedded systems microkernel with a capability-based security model. The formal proof happened originally in 2009. There's since been ongoing extensions to the capability and proofs. That's been demonstrated recently in a project, a DARPA project that's just finished, High Assurance Cyber Military Systems, which was deploying SEL4 into an unmanned helicopter. So at the beginning of the project, the red team could hack into the mission control system without too many problems. But by the end of the project, even though the red team was given the root password on the Linux, on Linux running on the same hardware as the mission manager, they weren't able to breach that isolation, and that's the sort of key thing that was provided here by SEL4. So you have to be aware of some of the limits of formal methods, so I'll illustrate that here. The limits here is that what you're doing is mathematical proof, and there's always some gaps. There's two gaps here. There's a gap between the lowest level of your formal model and the real world. So just because I've got a mathematical model of some code, does it actually correspond to what's going to happen with the real computer? And there's a gap at the top. So just because you've written some mathematics for a formal specification, is that actually going to correspond to people's real needs in the real world when they're using the system? So we can say, sort of, SEL4 is bug-free, but we don't say bug-free because what is a bug? That's not, people don't know what that means. Instead, we can write down some more specific properties. So it doesn't have any null pointer dereferences, it doesn't have undefined behavior, all the behaviors conform to the specification. But all of those properties only hold when these assumptions are true about the sort of operational deployment of the code on real hardware. So you're using the correct hardware and you've got the right boot code and you're not turning on direct memory access and so on. So when it comes to formalizing smart contracts on blockchain, we have the same sort of scheme here. We've got real people in the real world using smart contracts, and they've got real needs, and they're working often in real legal contexts. And at the bottom, we've got a machine that's executing bytecode, say, on a virtual machine, and that's a real physical machine distributed around the world, burning electricity, as we've just heard, on the mining network. And so in between, we've got all these sort of different layers of abstraction. So this here is a map of a few pieces of research that have been published over the past couple of years around formalizing and doing semantics for smart contracts and doing verification for smart contracts. I won't go into the details. There's some work about trying to do type-safe smart contract languages, often not Turing complete, to make it easier to reason about those. But you don't have to restrict yourself necessarily in that way. So there's also been people looking at models of Solidity and other more expressive languages for doing smart contract verification. And there's some work done which we're starting to get involved with is formalizing the Ethereum virtual machine, for example, at a lower level. There's some interesting, there's still these gaps that I talked about before, the gaps to the real user needs and the gaps to the real machine. There's a few nice things about blockchain for this lower level gap. So one nice thing is it's deterministic. The smart contracts have to be deterministic so you can get consensus across the mining network. But that makes the mathematics much easier as well, so that's nice. The immutability makes it easier to have assumptions about the stability of the data you're carrying through in your proof. But a key thing is that the mining network, it's not just getting consensus about the values of stuff on the blockchain, but you're also getting consensus or some sort of confidence in the integrity of your execution environment. So you have good confidence that everyone's got the same sort of model of what the virtual machine is, because they're all cross-checking each other's computations. So that's nice as well, because it directly addresses that gap at the bottom. So announced today, we've started contributing at Data61 to an existing project on the formalization of the Ethereum virtual machine. And so that's being done out of the same group that verified and is maintaining the SEL4 verification. And that's the URL. And that's being done in the Isabelle Hull Ethereum prover. which is also used in the SEL4 verification. We're bringing sort of two things to this. The first thing is looking at proof engineering. So this is our line of research trying to make it sort of cheaper and more scalable to do formal verification. And we're using sort of verified code frameworks that are meant to enable not just composition of code, but compositional reasoning about code, so you can do more scalable verification. We've got some approaches for doing formal decompilation. So in SEL4, we decompiled the ARM assembly code back up to C, and so that's part of the plan here, is we'll take the Ethereum virtual machine bytecode and decompile that back up to whatever language we end up targeting at higher level. And we're interested in understanding sort of metrics about formal verification projects to support things like estimation, but also to let us sort of do data-driven improvement of these proof engineering techniques. We'd also like to link the virtual machine up to sort of formal specifications of smart contracts. So we're thinking about that in a few different ways. So sometimes people say in the blockchain world, code is law. So we've got, so Lawrence Lessig was said, code is law, and that's sort of a mantra that's carried by a lot of people. There's also this traditional English saying, the law is an ass. And so using formal logic, we can deduce that code is an ass. And because it's an English saying, ass here means donkey, not the rear end of a donkey. This slide is meant to be saying, think of the DAO, for example. So the DAO, there was a white paper that described the DAO, and there was big disclaimers that said, this description of the DAO is not the DAO. If you want to know what the DAO is, go and read the code. The code is law, and that's the specification for what it should be doing. So that's, I think, a good example about why code is not a good specification. What we want are nice high-level properties that people can understand about what it is your smart contract should be doing. And this is, I think, an area that's not as widely researched and appreciated, I think, as it should be. The problem with a smart contract, with, say, a Turing-complete language, is not so much working out what it's actually going to do, but equally hard is working out what it should be doing and trying to write that down in a clear way. So at Data61, for example, we're looking at a variety of different ways of trying to specify smart contracts at a higher level of abstraction, and to use those higher levels of abstraction either as specifications for what smart contracts should do, or for sort of what often people call model-driven development, or domain-specific languages, or formal synthesis, to sort of generate smart contracts from these more abstract descriptions. So as I mentioned before, we've got some work on taking business process models in BPMN, transforming those into to smart contracts that can do coordination for inter-organizational process coordination and use the blockchain to run that engine. Similarly, schemas defined in things like ER diagrams or UML class diagrams, transforming those into smart contracts that implement registries. And both of those you can reason about the process model or the schemas at a higher level of abstraction and get some confidence that it has the kind of properties that you want for your smart contract without having to dive into the code necessarily at the bytecode level. The last area we have also a deep strength in legal informatics, which is creating logics that correspond to the structure of legal texts, so whether that's legislation or contract clauses. And so we're using that as a basis initially for thinking about the specification of smart contracts. Not every smart contract is meant to be a legal contract, but sometimes they are. And then this approach can be used to try and build a bridge between what we have as a smart contract and the legal world. So I talked at the beginning about trustworthy blockchain-based systems, and really smart contracts are just a small piece of that technology stack. A blockchain is almost always just a single component in a much bigger blockchain-based system, and there's always these other kinds of functionalities that are inherently have to run off blockchain. So key management has to be outside the chain. Interactions with the real world, like in IoT, or sometimes you don't want to put private or big data on a blockchain, that has to sit off chain. So all those kinds of integrations have to happen, and if you're developing an assurance argument for your blockchain-based system, you can't just focus on the smart contract. it's a good thing to be verifying because a lot of the design complexity for a blockchain-based system is going to sit inside the smart contract, and so you want to know that that's right, but you can't just focus on that alone. And also functional correctness is just one aspect of fitness for a system. So you also are concerned about lots of other non-functional properties for latency and throughput and so on. Formal methods are not necessarily such a great way of constructing that kind of evidence. So you need to combine formal methods with these other approaches. So overall, you want system levels assurance arguments about all of these different kinds of qualities. And then the next challenge, which I won't talk about today, is how do you get regulators to understand and accept that kind of evidence. So in closing, we need blockchain-based systems that work, but for dependable blockchain systems, we also need evidence that they're going to work. Formal specification verification can create really strong evidence, and it's becoming feasible to use this for real-world systems. But we need to understand and appreciate the limits of what the evidence brings us. So we're a global leader in doing systems code formal verification. We're starting now to contribute to the EVM formalization. If you'd like to help us accelerate that work, or if you'd like us to work with formal verification in some other smart contract platform, then come and talk to me afterwards. So I'll wrap it up there. Thanks very much. I think I'm early. If there's any burning question. No? Okay, thank you.